Good evening and welcome to our 7th lecture. We'll be discussing stability and frequency response of discrete time systems in the Z-domain. We'll start with the unit circle and the ROC and its implications on bibostability, as well as we'll take a look at some signals along the unit circle, the cosines and the sines. We'll introduce the frequency response of discrete time signals, and we'll focus on the magnitude plot and the phase plot. As you'd recall, we have the ROC to distinguish signals in the Z-domain. However, the ROC also dictates the convergence and stability of discrete time signals. In order for a causal signal to be stable, the rightmost pole of the system should be within the unit circle. For anticausal signals, the leftmost pole should be outside so that the ROC will include the unit circle. Let's take a look at some examples. So in this case, we're not given any ROC, so we'll assume 3 cases for the following signal. For the first case, we have a causal signal, and we'll see that if the system is a causal signal, it will be unstable, since the rightmost pole will be outside the unit circle. And if you plot this x of n in the time domain, we'll get an exponentially increasing discrete time signal. If you take a look at the two-sided case wherein the first term, point a to the n u of n, is the causal part, we'll see that the two-sided signal is stable. And if we get the time domain plot, we'll see that both on the right side and on the left side, both functions are decaying to 0. If both of the terms are anticausal, we'll see that the function or the system is unstable as it is growing exponentially towards negative infinity. Now, what happens when the pole is at the unit circle? If you'd recall, the ROC should not contain any of the poles of the system. Here are some examples of signals with poles at the unit circle. One is the unit step, which is a bibostable function. You also have the cosine and the complex exponential with magnitude equal to 1. Now, all of these signals are bibostable, which means that systems with poles at the unit circle are also stable, but we call them marginally stable because it is bibostable but unstable in a strict sense. And these signals does not decay to 0. It's either a unit step or an oscillating function. Evaluating signals at the unit circle will also lead us to the frequency response, since frequency response describes the magnitude and phase of the discrete time signal with respect to frequency. And if we recall, the complex exponential z, which is equal to re to the j omega n, is evaluated at r is equal to 1. And the frequency response is similar to a time domain frequency sweep or AC analysis, as we test the outputs of a discrete time system using these marginally stable signals, such as the sinusoidal inputs. Going back to our impulse responses, we've already classified 2 types. So one is the FIR, and in the frequency domain, it has this following form. And for the IIR systems, we have a rational expression with components in the numerator and the denominator. Now let's focus on the magnitude response. It's typically represented in decibels versus omega, or it's also denoted as the magnitude or absolute value of h of omega, or h of e to the j omega. To get the magnitude plot, we just need to get the relative distances of each of the zeros or poles from the unit circle while varying our omega, as shown here. So to demonstrate that, if we have this pole and 0, we just need to sweep within our unit circle at varying omega and get the relative distances of each of the terms from that point in the unit circle. If we have a system with 1 pole and 1 0 located at negative 0.5 plus 0.7 j and 2 plus 0.4 j respectively, we just need to get the relative distances of each of the terms at the unit circle e to the j omega as we vary omega. So here I tested 5 points at 0, pi over 4, pi over 2, 3 pi over 4, and at pi. So we'll be able to get, using this function in MATLAB, these distances. So what we need to do here is to multiply all the distances we got from the zeros and divide it by the products of all the distances in the pole. So here we get the magnitude on the last column. So as the omega increases, we'd see that the magnitude increases. And this looks like a high-pass filter. So these are the common magnitude responses of different systems. As you can see, our example previously is almost similar to this fourth graph, which has a pole on the left side and a zero on the right side, and it's called a high-pass filter. Now, these are the ideal plots of different filters. So for low pass, we have a cutoff frequency at omega c, and ideally, the system should have zero magnitude at frequencies greater than that cutoff frequency. Now, the inverse is true for the high-pass filter. We also have bandpass defined by omega 1 and omega 2, as well as the center frequency denoted by omega naught. And the inverse for this bandpass is called the notch or the bandstop filter, as shown here. We also have an all-pass filter. Later on, we'll discuss how systems benefit from these types of filters, especially on the phase response. Now let's try to get the magnitude response of a given moving average system. So here we'll just transform everything into the z domain and let z equal to e to the j omega. So here we'll get a closed form expression for the magnitude response. And if we plot this and sweep over omega, we'll get this following plot, which is a low-pass filter. The figure below is called the phase response. Now let's take a look at an autoregressive system defined by y of n equal to ay of n minus 1 plus bx of n. Now if we transform everything into the z domain, we'll get this following expression. And if we vary the parameters for b and a, we'll see that it's also a low-pass filter depending on the a and b parameters. Now the phase response is typically represented in degrees versus omega. And it's usually denoted by the argument or the angle of our transfer function h of omega, or h of e to the j omega. And here, we need to get the relative angle of each of the zeros and poles from the unit circle at varying omega. So before, we've expressed our magnitude response as the relative distances. Now we're getting the angle of our phasors. So to get the total phase response, we just need to add all the angles from the zeros and subtract all the angles from the poles. So in our previous example, we can obtain the relative angles by using the angle function in MATLAB, and we just subtract the zero angle from the pole angle to get the total angle. Manually, this can be done by getting the tangent inverse of the imaginary coefficient over the real coefficient. Now, ideal filters has a linear phase response. And what's good about phase response is that it rarely affects the stability of our systems. Now, if we have our input which is subjected to a system with a linear phase response, then we get an output that is just amplitude scaled and phase shifted version of our input. Now, in phase response, we also take a look at the group delay, which is the time delay that a signal component with the frequency omega undergoes as it passes from the input to the output of the system. And it's denoted by the following equation. For linear phase filters, since the phase response is just a linear function of omega, then we'll just get a group delay which is constant. For causal linear time invariant discrete time systems, it's ideal to have a minimum phase system since most of these systems are stable. Now, minimum phase systems have all zeros within the unit circle, while maximum phase systems have zeros outside the unit circle. Now, among all pole zero systems having same magnitude responses, minimum phase systems have the smallest group delay. And among all pole zero systems having the same magnitude responses, which means they have same total energy, the minimum phase system have the largest partial energy. So here is an example of two systems having the same magnitude response, but different phase responses. Now system 1 is a minimum phase system, while phase 2 is a maximum phase system. Now I'll be introducing some filter design concepts via pole zero placement. So for digital filter design, we want to place poles near the unit circle corresponding to frequencies that needs to be emphasized. And we place zeros near the frequencies we want to be de-emphasized. Now, in order for the system to be stable, we should place all the poles inside our unit circle. And our zeros can be placed anywhere in the z-plane. If we want to have real signals, we should have complex conjugate zeros and poles in our z-plane. Now for this example, we want to find B0 and P with this frequency response parameters. So first, we want to get the form of the magnitude response. And it's stated that the magnitude response at omega equals 0 should be 1. So we have this first equation. And the other equation is defined by the magnitude response squared at pi over 4. So using systems, we'll get this B and P parameter. Now here, we're tasked to design a two-pole bandpass filter with the following frequency characteristics. The first step is to define our transfer function with the amount of zeros and poles. So here we have two poles and two zeros, and the two zeros are already located at omega equals 0 and omega equals pi. So we have z minus 1 and z plus 1. Now for the poles, we can get it by evaluating the transfer function at these frequencies. So here we have our first equation here and our second equation below. So using our systems of linear equation, we'll get our value at our two poles, which are both complex conjugates of each other. So we'll get this bandpass filter. Now some notes on the filter design, we can actually convert a low-pass filter into a high-pass filter by implementing this particular operation. So we just need to invert our filter by subtracting pi to each omega. And effectively, what happens is that we multiply -1 to the n to our low-pass impulse response. We can also invert the poles and zeros of functions. Now, a system is invertible only if there is a one-to-one correspondence between its output and input signals, defined by this parameter. So, in summary, we've seen that discrete time systems are stable when the unit circle is included in the ROC. And systems with poles along the unit circle are called marginally stable systems. We've discussed the frequency response, which reveals the filter characteristics of a discrete time system in the omega domain. And it can be easily obtained by setting z equal to e to the j omega in our transfer function. And lastly, we've discussed some filter design concepts by the pole zero placement methods. For further reading, I'd recommend these chapters in our references. And that's it. Thanks for listening.